In this problem, we're looking at a material for which we know the Young's modulus. We also know that the material is in plane stress, so we just have sigma x and sigma y as our two normal components. We know what sigma x is, we don't know sigma y, but we do know that the change in length in the x direction, the change in length in the y direction. And what we want to do is calculate sigma y and also Poisson's ratio from that. So let's first write down some things that we know. It's given that the change in length of the specimen in the x direction is a positive 0.00176 inches. And the change in length in y is a positive 0.0344 inches. So therefore, what we know is that epsilon x, which is delta Lx, divided by the value of Lx that we have. So that is a known, and keep in mind that that's a plus because delta Lx is positive. Same way here for the strain. That's delta Ly divided by Ly. Again, that number is going to be plus because we have a positive value there for delta Ly. So we're going to go back to our Hooke's law, or stress-strain relationships, which says that epsilon x is equal to 1 over e sigma x minus nu times sigma y plus sigma z plus alpha delta t. Epsilon y, strain in y, is equal to 1 over e sigma y minus nu quantity sigma x plus sigma z plus alpha delta t. We're not running these tests under changes in temperature kind of conditions. Since it's in plane stress, we have sigma z equal to a 0. So from these two Hooke's law equations, we can say that epsilon x times e is equal to sigma x minus nu sigma y, and we have e times the strain in y, both of those we know, and that's going to be equal to minus nu sigma x plus sigma y. So what we want to find out are nu and sigma y. So we need to figure out a strategy for determining those. I'm going to call this equation 1 and equation 2. What you would see here is that if I would multiply equation 2 by nu and add that to 1. And what that will do is it will get rid of the appearance of this product term there of nu sigma y. So again, that's going to be e epsilon x plus nu e epsilon y is equal to sigma x minus nu squared sigma x. And again, our goal there was to get rid of sigma y in those equations. So from this, what we can do is solve for the Poisson's ratio. What I'm going to do is bring everything over on one side. I've got a nu squared times sigma x. I'm going to have a term here of nu times e epsilon y. And I'm going to have as my other term here is going to be e epsilon x minus nu x equal to a 0. Basically, I have a quadratic equation in terms of nu squared, so I'm going to divide through by sigma x. I got e epsilon y sigma x times nu plus e sigma x minus, epsilon x minus sigma x divided by sigma x equal to a 0. So I got the quadratic equation in a standard form, so I solve using the quadratic equation. So that's minus E, the strain in Y, which we know, the stress in X, which we know. We know we have two roots of the quadratic equation. So E epsilon Y divided by sigma X squared minus 4 times E epsilon X minus sigma X divided by sigma X, all divided by 2. Again, we have two roots. So in the end, what we will do, we'll find one root will be positive, one will be negative. So what we will do is keep the positive root. So once that's done, then we can go back to, let's say, equation 1. At this point, we know everything from equation 1 except for sigma y. So that's going to be sigma x minus E epsilon x divided by the value of nu that we just found as that. So again, we're given sigma x, we're given E, we're given information on epsilon x, and this here should have been a, I think I wrote that down wrong. I said it right, I think. But this should be, from equation 1, should be divided by nu, and we just found nu. Sorry. What we have here is just a case where we're applying Hooke's law again. In the case of plane stress, we know that sigma z was equal to 0. The tests were run under constant temperature, so we don't have the thermal effects. And we basically had two equations here, 1 and 2, in terms of two unknowns. Just a matter of solving those two unknowns. In this case, we knew everything except nu and sigma y.